So the last couple days you've been working with differential equations, and you've learned how to separate and integrate those to come up with their solutions, and if given a plus c, then you were able to find a particular solution. So today we're going to learn how to make a graph of a differential equation, and the graph of a diff EQ is something that's called a slope field. A slope field is not a connected and fluid graph. It is not continuous. It is made up of discontinuous segments at different coordinate points. And so you've given a sample of a slope field graph right here, which contains 9 different coordinate points. Only the 9 that are picked out on this one. And so what we're going to do is create the picture of what is called a slope field. It's not hard to do. You just do it one point at a time. So let's start with the first point up there in quadrant 2. Let's just look at the point -1, 2. At that particular point, we'd like to know what the value of the slope is. Well, we have an equation for the slope. It was given right here, dy over dx, which tells us what the slope value is. So we're going to plug the coordinates of the point into that. So that would be 2 minus 1 over -1 squared, which works out to be 2. So that means that this coordinate point here, we're going to draw a segment of a slope that has a value of 2. Okay, so something about like that. All right, if you were estimating, right, a slope of 1 would be more of a 45-degree angle. So a slope of 2, it's really kind of eyeballing it, but you're doing your best to come up with what the value of that slope is. And so let's work our way down. And let's look at the next coordinate. And so let's look at -1, 1. And so using the same process, we'll plug 1 minus 1 over -1 squared. This time we get 0 as our value, which means my slope here would have a horizontal segment of 0. And then the one right beneath that, -1, 0. So we'll get 0 minus 1 over -1 squared. So that would be -1. So we will graph, a slope of -1, which is pretty much a 45-degree angle, sloping downwards. So those are the first 3 points of what's called the slope field. And you do that for all 9 points in this particular slope field value. Turns out, okay, let's work on the next couple. So let's do 1, 2. So that would be 2 minus 1 over 1 squared. So that's going to be 2 again. The next one at 1, 1 would be 1 minus 1 over 1 squared. So 0. And then bottom one down there, 1, 0. That would be 0 minus 1 over 1 squared. That would be -1. So you can see we got the same answers that we did the first time. All right, let's do the last set. And so I'm just going to save myself a little time here by changing. I know the y values are going to stay all the same, but the x values will be different. And so this would be 2, 2, 2, 1, and 2, 0. So 2, 2, there we go. Change all of the x values, and that will change the result. So I'm going to get 1/4 this time. I'll get 0 again for the second one, and I'll get -1/4. All right, so 1/4 is pretty slanted, 0, and -1/4. everything that had a y value of 1 ended up with a horizontal piece. Everything that had a y value of 2 was some kind of positive number. And then everything with y value of 0 along the bottom had some kind of negative slope. Now it's interesting to look at these two and to think, what would all the slope pieces be in between there? That slope was, the original slope was 2, and they probably are all kind of tilting sideways a little bit more until you finally get to 1/4. You know that that's going to be 0 no matter what. And then these are probably tilting a little bit more. By thinking about that, you can tell the concavity. This section here, it will always be positive, but the slopes are getting less and less with a value. They're still positive, but they're decreasing. So therefore, that's going to have concave down nature. This section down here, they're always going to be negative, but less and less so. And so they are negative, but they are increasing. And so that's going to be a concave up section. No matter what here, you're always going to have a horizontal piece, because no matter what, the y value being 1 is going to always make your numerator be 0. So those are things that you can, the slope field's not hard to create, but looking at the slope field and determining the positive and negative nature of the slope, also the concavity is a skill that you'll practice. The second parts of this FRQ are ones that you've been working on for the last several days, finding a particular solution. So here's where you come up to the separate and integrate part of this equation. And so looking at the diffie-q here, we would separate that so that we could integrate it. So it would look like dy over y minus 1, and then it would look like dx over x squared. And so then you're ready to integrate that. This is the natural log of the absolute value of y minus 1 plus the first constant. The other side is not the natural log. Sometimes people mistakenly think that, oh, it must be the natural log of x squared since I did the natural log on the other side. But that's not true. Okay, the correct way to think about that integral is to remember what x squared actually means. Okay, so we're going back to x squared over 2. Maybe be better to think of that as x to the negative 2 dx. That way when you integrate it, you get x to the negative 1 divided by negative 1 plus your second constant. So we're looking at the natural log of the absolute value of y minus 1 and negative 1 over x plus the overall constant c. Now we're going to solve for c using the initial condition here that we're given, where x is 2 and y is 0. So the natural log of the absolute value of 0 minus 1, negative 1 over 2 plus c. You can see how it's important to have the natural logs. Important to have the absolute value in your natural log, because if not, you'd end up with the natural log of a negative number. So we want the natural log of the absolute value of negative 1, which is the absolute value, which is natural log of positive 1, which is e. Okay, and then 0, which is 0. Okay, and then negative, we've got negative 1/2 plus c. So c turns out to have a constant value of 1/2. So if we put all that together, running out of room here, we'll have the natural log. Maybe I'll do it over on the side. The natural log of the absolute value of y minus 1 equals negative 1 over x plus the constant 1/2. So we'll apply e to both sides. That'll give me the absolute value of y minus 1 equals e to the And as a whole quantity, negative 1 over x plus half. And then when we take the absolute values away, we've got plus or minus the quantity e to the negative 1 over x plus half. And then y equals plus or minus e to the quantity negative 1 over x plus half plus 1. Now we look at our initial condition, because to decide if we're going to keep the positive or the negative, we can't keep both because this has to be a function that passes the vertical line test. So looking back at the original condition, we see that if we plug 2 in, we should end up with 0. So let's see what happens when I plug 2 in here. Plus or minus e to the, okay, I'm going to plug 2 in, that would be negative 1 half plus 1 half plus 1. That's plus or minus e to the 0 plus 1. And we know that this is supposed to come out to be 0 because of the initial condition. Plug 2 in, you should get 0. So should it be plus or minus e to the 0, which is 1 plus 1? Well, it's got to be the negative. It's got to be, the only way to make 0 is to have negative 1 plus 1. So then that helps us know, once we've thought about that, that the original solution, that the actual solution to this would be the negative solution. Okay, you've got to decide one or the other. You can't leave it as both. I always base it on the initial condition. Okay, let's go on to the second example. This one has 12 points indicated, but you're going to create the process the exact same way. So just looking at, maybe we'll start with that one again. And so that would be the point negative 1, 2. So negative 1 goes in for x, 2 goes in for y. This time we get negative 2 times negative 1 over 2. That's 1. So we're going to have a slope of 1. And then you work your way through each point. Let's see, negative 2 times negative 1 again, this time over the y value of 1. So that would be 2. So a little bit steeper than what we had before. Okay, how about we move down to these quadrant 2 values. Okay. Negative 1, negative 1. That would be negative 2 times negative 1 over negative 1. So this time we get negative 2. And then the bottom one, negative 1, negative 2. So now we're going to get negative 2 times negative 1 over negative 2. So this time we get negative 1. So the bottom quadrant, those in quadrant 3, is always going to be negative. No matter what you do, it will be negative, but it will be increasing. The farther down you go, the slopes will be increasing. So this is going to be concave up, whereas in quadrant 2, it's concave down. Let's see if we can check that out all the way. I'm going to change all my x values here. I don't have to rewrite everything. So let's do 0, 0, 0, 0. So I'm just changing all of my x values. And look at what happens. all the x values are 0, then all of the slope values are also 0. And so all of these pieces will have a 0 horizontal slope. Notice I'm not doing any of the points where y is equal to 0, because that's not part of the domain of the differential equation. We can't have y in the denominator. Right, and then moving on to the last section again, the quickest way is just for me to change all my x values. And I'll change them all to 1 this time. 1, 1, 1, and 1. So I end up with negative 1, negative 2, positive 2, positive 1. So the reverse of what I had before. So if I was trying to picture what's going on at some of the other points, maybe, they're getting flatter and flatter until we get to plate flatness, and getting, again, flatter and flatter and flatter and flatter, because I can see the concavity is concave down when I'm above the x-axis, and when I'm below the x-axis, it's the opposite effect, so concave up. All right, part B, again we have a particular solution, and we're asked in part B to find a tangent line, and in part C to find the particular solution. So anytime we do a tangent line, we need a point and we need a slope, and they're asking us to do it at 1, 1. So we've got part B, we have our point. Our point is 1, 1. We've figured out the slope at 1, 1 to be negative 2. So we write a tangent line, y minus 1 equals the slope of negative 2, x minus 1. We're going to use that tangent line to approximate 1.1, which we're going to plug in for x to come up with the approximation. So y minus 1 would be negative 2 times 1.1 minus 1, which is just basically 2 times a tenth. So negative 0.2. Add 1 to both sides. Okay, when you add 1 to both sides, you get 0.8. And so we are estimating that the approximation for 1.1 on the graph would be 0.8. Then to find the particular solution, you're going to separate and integrate again. And I've run out of white space, so I'll just do it over here on the side. We were given dy dx equals negative 2x over y. So we'll separate and integrate that. So y dy and negative 2x dx. This is not too bad of 1 half y squared negative x squared plus the constant of c. I want to find my c using my initial condition, which was given, negative 1, 1. So negative parentheses, negative 1 equals 1 half times 1 squared. So we're looking at 1 half equals negative 1 plus c. In other words, c is equal to 3 over 2. So now we have 1 half y squared equals negative x squared plus 3 over 2. Multiply everything by 2. and then do the plus or minus. So y is equal to plus or minus, I think I'm going to write it as 3 minus 2x squared, just looks a little better. All right, so it's either the positive or the negative. I have to decide. Again, you look back to your initial condition. The initial condition was that when you plug 1 in, you have to get -1 as an answer. Well, I can tell right away, the only way for me to get 1 is for me to keep the negative portion. And so I will keep negative square root of 3 minus 2x as my solution, my particular solution. Okay, I hope that gives you a good introduction to the basics of a slope field, and then how it's connected to a differential equation and what you can learn about a slope field. In the next coming days, I'll show you how there's a feature on your calculator that we can use to create slope fields as well that are a little bit more complete than the ones we would do by hand, because it can do a lot more decimal points or a lot more coordinate points a lot faster than we can. So I hope to be back with you tomorrow. All right, see ya.